which we want, one of them becomes real, and the other one is
So there's two outcomes.
yeah.
Anybody want to help them out? What are those two outcomes?
One which we want to happen.
Okay, so a bit more specific. What do we call that? If we want it to happen, we say it is a success.
Okay.
Right? So what's the other outcome got to be?
Fail.
Perfect. So yeah, two outcomes that basically boil down to it either happens or it doesn't happen.
Yeah.
Right? So success or failure. Right? Okay, specifically, what's the other thing that we need? So when we get given a binomial distribution, we also get given a probability. Yeah, good. Okay, that's the other thing I wanted. Yeah. So number of trials. Okay. So the number of trials we denote by the parameter n.
Yeah.
Right? We also get given a probability with a binomial distribution. Now, what is that probability? Is it success or is it a failure?
Both of them.
No. So if I tell you that I have a binomial distribution, so let's say binomial distribution with the number of trials being 10 and the probability of something is 0.3.
Okay.
What is that probability corresponding to?
In 10 tries,
Uh-huh.
the probability of getting success.
Perfect. That's what we have.
Yeah.
Okay, so that parameter there, that probability, is always to do with success. Okay, never failure, right?
Yeah.
So even if we define our random variable, this is why it's really important to define the random variable. If we define our random variable as the number of missed goals, ordinarily you say, well, hang on a minute, they didn't score the goal. Isn't that a failure? Not in this case, because the way that we're defining that probability, the way to define the probability, or the distribution rather, is that we're doing it 10 times, we're kicking at the goal 10 times. The probability of missing the goal is 0.3. So in that case, it's the probability of missing is our success, right?
Yeah.
Whereas obviously going in is the failure in that case. Yeah. So it all depends on how we define it, yeah. So you sometimes see this written as Q, which is 1 minus P, obviously.
Yeah.
Okay, so that's really the two parameters that we need to consider when we're dealing with a binomial distribution, okay? Obviously, we have all of the different sort of characteristics, such as, for example, independent trials and various other things that needs to be discrete and such like. But yeah, so binomial distribution is that. So what's the difference between that and a Poisson distribution? Okay.
Yeah, I don't know this one. Well,
All right. So it might help if I actually tell you what the distribution is. So actually, let me just get rid of that. That's just an example.
yeah,
That's NMP.
the notation is lambda.
Good. And what is lambda?
Oh, lambda is lambda.
It's the rate of occurrence, exactly, occurrence or success. Okay? So rate of success, rate of occurrence, whatever you want to say from that. So really, it's quite nice in this course, you only have two distributions that you really need to worry about with discrete. Obviously we have normal distribution as well. Hopefully that's a bit more obvious that it is a normal distribution. But yeah, if you have a discrete distribution, I'm not necessarily going to sit there and say, hey, look, this random variable is modeled using a binomial distribution or modeled using a Poisson distribution. I'm expecting you, from the way that I phrase the question, to be able to establish that yourself, right? So if you have two outcomes, success or failure, and a fixed number of trials, I should say that's fixed number of trials because that doesn't change, then we're talking about a binomial distribution. If I'm just talking about a rate of success, for example, the number of people that walk through that door in the next hour is 6. That can be modeled using a Poisson distribution because it's a rate of success. In other words, the crucial thing here is that you're nearly always going to be given a time frame. Okay? So the number of people walking through that door in the next 5 minutes, or the number of heartbeats in the next minute, or the number of people that tweet about Donald Trump in the next day. right? It's always got a time in there as well.
Rather than number of tries,
Good.
there is time.
Good. And I mean, we talked a lot about this binomial versus Poisson distribution. Actually, as it happens, the Poisson distribution is just the limiting case of a binomial distribution. So in other words, as you increase the number of trials, the Poisson distribution starts to take shape. And then obviously as you increase them even more than that, you get continuous distribution, which then where the normal distribution comes from. Okay. But yeah, exactly that. The Poisson distribution doesn't have a fixed number of trials. It just has a rate of success. Okay. And obviously rate is to do with time. So to be honest with you, if you wanted a kind of just a takeaway from this, a good rule of thumb, if you like, a Poisson distribution, if you see time involved, right? So if you say the number of people that have, I don't know, a particular disease walking into a hospital in the next 5 minutes, right?
Yeah, exactly.
So that's got time involved. It's not got a number of trials. You know, I wouldn't worry too much about the outcomes because we're still talking about successes down here. Make sense?
Exactly.
Cool. And then, yeah, like I say, if you've got a continuous distribution, chances are in this course it's going to be normal, right?